All right, guys, I'm going to go over chapter 5 notes. I'm only going to do the first half for now, and then I'm going to do another video for the second half. But we're talking about discrete probability distribution. So if you remember, discrete was when it's countable or it's not continuous. And again, we're going to do some basic concepts first. So a random variable is a variable typically denoted with x that has a single numerical value determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value of the random variables. So probability distribution is how is each x value go ahead and spread out or distributed. It is often expressed in the format of a table, which we're going to do on this, a formula, which I am going to give to you, or a graph, which we don't really focus on in here. All right, some definitions that you should already know are discrete random variable. It's a collection that is finite or countable. So an example of this would be something like flipping 5 coins and seeing or getting 2 heads. Like, it's countable. I can flip a coin 5 times and I can get 2 heads. And a continuous random variable has infinite many values, and the collection values is not countable. And if you think about, again, back from chapter 1, an example would be like body temperature. And there's a lot more examples in the first chapter 1 notes. Probability distributions, the requirements. And I'm going to have you guys go ahead and like write down, memorize, or remember, or make note of. You're going to need to know these 3. So the first one is every x has to be between, so every x has to be for between 0 and 1. So we're going to write the probability has to be between 0 and 1. And you saw that in chapter 4. Every probability should be between 0 or 1. The next one is going to be the sum of all probabilities. And you guys know this. If I add all the probabilities together, I should get 1. And the way you actually write this, and I'm going to actually use a lot of symbols, is this is the summation sign of all of the probabilities should equal 1. So the sum of all probabilities equals 1. And the third one is it has to be numerical data, or as you guys know this as quantitative data. Data. I'm going to write not categorical. All right, so we're going to go ahead and do a problem. So it says, let's consider tossing 2 coins, which are the following random, with the following random variable. So x is going to be the number of heads when 2 coins are tossed. Now, before we even start, let's go ahead and write out all the ways 2 coins. What are my options I can get? So I can get 2 heads. I can get a heads and a tails. I'm going to get a tails and a head, and a heads and a heads. And you guys saw this again the last chapter. So it says create a probability distribution for random variable. Okay, so if I say create a probability distribution, you can do a table, a formula, or a graph. I'm going to do a table for this one. So I'm going to write x and the p of x. So what does x stand for? Well, x is whatever I wrote. I wrote x is the number of heads when 2 coins are tossed. So if I look at this, what is the minimum number of heads I see? Oh, I totally messed this up. There should be 2 tails. Sorry. How many total heads do I see? I see the minimum is 0 heads. Then I see 1 head. And then I see 2 heads. Now for here, a little trick is you always start with 0, and you always go to how many coins are tossed or how many like dice are flipped or rolled and all of that. So what is the probability that you get 0 heads? So only this one has 0 heads, and so that's the answer of 1 out of 4, or if you want to write 0.25. Again, either or is fine. You don't need to do both. What is the probability of getting one head? So one head is in this one and this one. So it's 2 out of 4, or 1/2, or 0.5. Again, you don't have to do both, you just have to do one. And the last one is what is the probability of getting 2 heads, which is only this one. So it's 1 out of 4, or 0.25. Okay, then it says check the 3 requirements. Order of these don't matter, but for each variable of x. Okay, so the first one is every x is between, the probability is all between 0 and 1. So I'm going to say all probabilities are between 0 and 1. Check. The second one is if I add all the probabilities, so 0.25 plus 0.5 plus 0.25 is equal to 1. Check. Notice I am literally showing my work for this. A little side note is for this one right here, you can get like 1.001 or 0.999. Like if you're close enough, that's fine. As long as you're close, it doesn't have to be completely like exactly 1, and that's just because of the rounding situation. And the third one is that, is it numerical data? Yes, it is. And so we're good. It says check all the requirements. I did. Okay, and I would ask you something like this, like check the requirements. Is x a random variable? Is it discrete or continuous? Explain. So x is this part right here. Is this countable or is it going on forever? Well, it's countable, so it's discrete because there's only 3 possible values for x. 0, 1, 2, 3. Oh, 0, 1, and 2, which is countable. And that is the end of the first set of notes. Okay, moving on. All right, create a probability histogram for the distribution above. Now, I know this page went off to the other side, but we're gonna go ahead and create a histogram. So remember, a histogram is there's no spaces in between, and we're doing it of the distribution. So this is gonna be percentages. Now, if you think back, our smallest one was 0.25 and our biggest one was 0.5. So I really only have 2 levels. And then the bottom was the number of heads. So when I do this, I have 0, 1, and 2, and that's pretty much it. And so when I graph this, I knew 0 was the 0.25, and 1 was 0.5, and 2 was 0.25. What is this graph, or what is the shape of this graph? This is going to be symmetrical. It's not skewed left or right, so it's symmetrical, and there you go. The probability formula. You're more than welcome to use this. The formula is 1 over 2 times 2 minus x factorial times x factorial. Okay, so it's always going to be this formula. It's not going to change. We're going to go ahead and have practice with it, and then I'm going to have you guys try 2 of them out, and I'll write out the answers. But you guys are going to do them if you want to do them. So the first one we're going to do is P of 0. So this right here is your x value. So these are each of your x's. So you're going to do the formula 3 times. So the first one is P of 0 equals, and I'm just going to plug in 0 every time I see an x in it. So 1 over 2 times 2 minus 0 factorial times 0 factorial. And I'm going to go ahead and simplify that. Now we know the answer is 0.25 because of the previous page, but we're going to go ahead and solve it. So 1 over 2 times, well, 2 factorial, 2 minus 0 is 2, and 2 factorial is 2 times 1 times, and then 0 factorial. Remember, that was one of the cases in chapter 0 that you need to know. That's 1. So the answer is 1 over 2 times 2 times 1, which is 4, which is 0.25, which is what we actually got in our chart, if you look at your chart. Okay, so I'm going to have you guys try out 1 and try out 2. The answers are 0.5 and 0.25, so see if you can get those values. Okay, let's go ahead and go on to example 2. It says hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table below are their responses. Does the table describe a probability distribution? Why or why not? Okay, so when I say does it, we have to actually like check requirements. And yes, I want you to check all three of them, even if one of them is not true. You don't have to say the first, like you have to check all three. So the first one, are all the probabilities between 0 and 1? Yes, all probabilities are between 0 and 1. Number 2. Let's go ahead and add them all up. So I already added them up, but you get 1.57. That's the total. Now remember, the number has to be 1 or close to 1. That is not close to 1. So we're going to say sum of all probabilities is 1.57, which is not 1. Okay, and the third requirement is that it had to be quantitative data. Is this quantitative data? No. So we are given categorical data, not quantitative data. Okay, so is this a probability distribution? So overall, no, because it doesn't meet all three requirements. So it's not a probability distribution. Get used to writing a sentence. Can't emphasize that enough. You will be writing a sentence from almost every single question now. All right, moving on. Parameters of a probability. So think about it. Parameters. Now, just parameters go with population or sample. Again, this is from chapter 1. It goes with a population. All right, what are my formulas? Well, mean. If it's a population, my mean is going to be mu. My variance is sigma squared, and my standard deviation is sigma. Okay, there are formulas to each of them. So your mean is going to be the sum, and that's what this symbol is, the sum of x times p of x. Okay, so it's going to be the sum of all values of this part. And again, we're going to do an example. What is the variance? Well, the variance, if you think about it, remember the tedious way to find the variance? It's the sum of all your x values minus your means squared times your probability of x. And that's really what the difference is, this times probability of x. We don't have to divide by n minus 1 or n. That is your formula. Now, how do I find my standard deviation given my variance? I go ahead and I square root it. So we're going to take, so sigma is equal to the square root of your variance. X minus mu squared times p of x. Fun times. All right, so let's go ahead and do an example of this. And this is where a graphing calculator or a calculator is very handy, okay? Again, you can use online stuff, but you need to go ahead and make sure you have a calculator that does all of these things. The last part is the expected value. This only works with the discrete random variable. So expected is what do you expect to actually get? So a discrete random variable is x is denoted e. Is the mean value of all the outcomes. So it's the average of all your outcomes. So E is actually your mean, if you think about it, because it's the mean of everything. So E it can also be found by evaluating the same way as you find your mean. So sigma, sum times your x times p of x. Okay, so let's go ahead and try an example. It says, looking back at example 1, which was the coins tossed, and the probability distribution, which we created that chart, for the number of heads when 2 coins are tossed. Find the mean, the variance, and the standard deviation for the probability distribution. So if you look at your chart, I'm going to copy down the chart in just this part. So my chart was 0, 1, and 2. And my probability was 0.25, 0.5, and 0.25. All I did was copy the chart from this. If I add all these numbers up, you get 1, which is good. Now, to find x times p of x, well, you have your x here and you have your p of x here. So what do I have to do with these numbers? Is I have to multiply them. So I'll write the first one out. So it's going to be 0 times 0.25 Well, what's 0 times 0.25, or 0 times anything, is 0. What's 1 times 0.5, which is 0.5? What's 2 times 0.25, which is going to be 0.5? Now, if you actually add all these numbers up, well, 0 plus a half is 1 whole. This right here is your mean, believe it or not, because if you think about it, your mean formula is this. And when you add them up, you're actually finding the sum of them. So your average is 1. This right here, now can anyone tell me what formula this is? Okay, this is your variance. Okay, but what do you have to do with all of them is you have to add them all up at the bottom. So all I'm going to do is I'm going to plug in my equation into this chart right here. Now I create a chart because it's so much easier to read rather than doing this for each single time. So your x is right here. So I'm going to do, again, I'm going to just do the first one. 0 minus your mean, which is this value right here. And you can't do this part without finding the average. Squared times your p of x, 0.25. All right, so 0 minus 1 is negative 1 squared, which is 1, times 0.25 is 0.25. You're going to do this for all of them. So you're going to do 1 minus 1 squared times 0.5. Well, 1 minus 1 squared is 0, so this is going to be 0. And then the last one is going to be 0.25 as well. So check it out, see if you get that. Now, if you add them all up, well, a quarter plus 0 plus a quarter is 0.5. And this right here, if I add them all up, this right here is your variance. Now, how do I find my standard deviation? Well, it's just the square root of the variance. So sigma is equal to the square root of 0.5. Now, I like rounding to 3 decimal places, at least 3 decimal places, so you get 0.707. And that's right here, your standard deviation, if you want to label that. How did I get that so fast? I know my square root of 0.5. All right, so interpreting. Now, this is where you write your sentence. Okay, so I'm just going to write a general sentence. So what was my example? It says when tossing 2 coins, or 1 coin 2 times, when tossing 2 coins, the mean of getting heads is 1. And I got that because the mean is 1. The variance is 0.5 and the standard deviation is 0.707. Okay, some rule of thumbs. If you actually remember again from the last chapter, we had the rule of thumb as mu plus or minus 2 times sigma. Anything bigger or smaller than that is significantly high and significantly low. So let's go ahead and go through this. So significantly low are values that are mu minus 2 sigma or lower. And what does this mean? It means that it's 2 standard deviations below the mean. How about high? Well, it's the same thing except it's the plus part. So values that are mu plus 2 sigma or above. And what does that mean in terms of words? It's 2 standard deviations above the mean. Values are not significant. So significantly high, significantly low. When is it not significant? It's when it's in between. So between mu minus 2 sigma and mu plus 2 sigma. So I'm going to give you guys a diagram. I took, again, all of this from your book. So if you want to look at your book, you can. This chapter was actually pretty decent in the book. So I'm going to draw a little arrow, and bear with me. I can't draw. You guys know this already. I'm going to keep drawing an arrow. Again, I took this from your book. That's my arrow. So what number goes in the middle? Your number in the middle is your mean. This is 1 standard deviation above the mean. And this is 2 standard deviations above the mean. And this is 1 standard deviation below the mean. And then this is 2 standard deviations. This should be below the mean. Okay. So this part right here in this part right here, anything above 2 standard deviations and anything below 2 standard deviations this is significantly high and this is significantly low. Okay, what about the part in between? The part in between is called not significant. Okay, and again, feel free to pause the video and try it out yourself or watch it and then try doing the example. It's really up to you. Okay, all right, moving on. Let's go ahead and do an example. Okay, so continuing the example of tossing 2 coins, the mean heads was 1, and we got this by the last time we did this, and the standard deviation was 0.7. I only did it to 1 decimal place, but again, remember 3 decimal places. Use those results and calculate the range of the rule of thumb to determine whether 2 heads is significantly high number of heads. Okay, so first thing I'm going to do is I'm going to go ahead and calculate, and I'm only asking for the high values, is I'm going to calculate the significantly high values, which is mu plus 2 sigma. Well, I gave you my mu, you found that, and you were given standard deviation as 0.7. Well, it's technically 0.07, but we're going to go ahead and calculate that. So this is 1.4 plus 1 is 2.4. So this number right here is anything above it is significantly high. Well, I gave you a value. I gave you 2. Is 2 higher than 2.4? No, it's not. So when you interpret the results, well, based on these results, we can conclude that 2 heads is not significantly high because it's not above 2.4. It's below it, and I'm only asking for significantly high. Again, that's a perfect sentence. Okay. Identifying results with probabilities. So we're going to be talking about the 5% rule, but in a significantly high number of successes is X successes among N trials is, I'm not writing the word significant, but I'm writing sig high if the probability of X or more, and I know it's more because it's significantly high, is less than or equal to 0.05. Okay. This number, well, again, we'll see this more later on, but this is called the 5% rule. Okay. Now, low is actually the same thing. It's going to be X successes among N trials is significantly low if the probability of X or less is less than or equal to 0.05. It's the same rule. Okay, so still 5% rule is just the X or more and X or less. So is 252 heads in 460 coin tosses significantly high number of heads? Well, first of all, significantly high, this is your formula. What's our mean? Well, I didn't give it to you, so we're going to have to go ahead and we're going to learn it in the next section, but I'm just going to tell you how to set this up. So we're going to do the probability of 252 or more heads equals 0.0224, and I'm going to have you guys go ahead and label this learn in next section. Learn in 5.2 notes. Okay. I just wanted to go over this value. Okay, so is 0.0224 less than or equal 0.05? Yes or no? Well, I'm only getting this number here. So which one's bigger? Well, this one's bigger. So is this true? Yes, it is. So if it's true, what is our answer? We can say we can conclude that 252 or more heads is significantly high because 0.0224 is less than or equal to 0.05. And that's, again, a simple sentence. Okay, let's go ahead and find expected values and rationale for formulas, a real life application. So I know some of you guys are over 21, so this is kind of like a cool little roulette versus craps. So you have $5 to play on a bet in a Golden Nugget Casino in Las Vegas. You have narrowed your choice to 2 bets. So this is the first bet. You have a roulette, playing roulette, and you bet on the number 7 in roulette. So if you don't know anything about a casino or roulette, it's okay if you don't. I kind of stole this from your book. Is you have 36 numbers. You have 18 red and 18 black. But then you have something, and that's where probabilities get all mixed up, is you have 0 and 00. And this is called green. And if you look at a roulette table, you'll see this. So what is the probability of losing? Well, how many 7s are there in a roulette table? There's only 1. Okay, so the probability of losing is, well, let's see. The probability of winning is 1 out of, and it's not 1 out of 36 anymore. It's 1 out of 38 because of the double green. Okay, between the zeros. Okay, so the probability of losing is, well, 37 over 38. Because the probability of winning is 1 out of 38. So the probability of losing is 37 out of 38. And what are you going to do? You're going to lose $5. Okay, what happens if you win? So this one's going to be winning. Well, what the probability is 1 out of 38. Okay, and what are you going to win? Now, again, this number is given to you, but the probability, if you bet $1 and you hit the number that you bet on, you win $35. Okay, you technically win $40, but you bet $5, you win $35. Okay, so if I bet $1, I win $35. What happens if I bet $5? Well, how do I find that value out? Well, I multiply 35 times 5, and I get 175. Okay, this is how much I win. You're like, yeah, but the chance of winning is very low. Okay, now that's the first bet. I have the second option of betting on the pass line in a dice game of craps. Again, I give this to you. Pass line, it's okay if you don't know your craps. I just thought this was a cool example of like you thinking about, I guess, gambling. Okay, so the probability of losing is 251 over 495. How do I know this? I looked it up. I didn't know actually this probability, which if I write in a decimal is 0.507. If you think about it, that's very close to a 50-50 shot of winning or losing. Okay, going on to the next page, the gain, net gain. The net gain is if you bet $1, you win $1. Okay, so if you bet $5, you win $5. So you win an extra $5. You don't just win the $5, you win your $5 plus more. All right, so your net gain is, well, if you're losing is 251 out of 495, your winning is 244 out of 495. And again, I got that by looking it up. Okay. Okay, which of the preceding 2 bets is better in the sense of a higher expected value? So we're going to say which one's better. Okay, so again, my events are you win or you lose. Now notice that's not my X. My X value is how much money I win. So my X is if I win $175. And if I lose, well, if you lose your money, how much did you bet? You bet $5, so you lose $5. Okay, what is the probability? Again, for winning, there's only 1 out of 38. Okay, it's not 36 because of the 2 zeros. And then losing is 37 over 38. So what is your X times P of X? Well, you guys, again, how do I find that? Is you multiply these 2 numbers together. And this is money, so do I round to 2 decimal places or 3? Well, if it's money, it's 2. So this is going to be, I win 461. Okay, and my losing is if I multiply these numbers together, I lose 487. Okay, so my total, well, if I add these up, I get 1, which is good because you always want to add 1. And if it's really this number that I care about. If I add them all up, Okay, if I'm adding them all up, I lose 0.26, or I lose 26 cents. Okay, this right here, if you think about it, this is your mean formula, or if you think back to your expected, this is your expected formula. They're exactly the same thing. Okay, so I'm gonna write a little sentence. It says the expected value is negative 26 cents, which means for every $5 you will lose, or you will be expected to lose 26 cents. You're like, then why would you ever bet? Well, that's what a gamble is called. Okay, so this is for roulette. Now let's go ahead and do craps. So again, craps, there's two events. You're either gonna win or you're gonna lose. So if you win, well, I wrote the probability up here, is 244 over 495. And if you lose, I wrote it on the other page, which was, sorry, this should be over here, 244 over 495. And if you lose, it's 251 over 495. What's supposed to go here? Well, how much money you make. So if you win a net gain of $5, and if you lose $5. You're like, okay, well, I win and I lose. This is, think about it in terms of, I guess, betting. So what is your x times p of x? Is if I multiply these out with a calculator, I get, and again, it's 2 decimal places, so I get $2.46. Okay, now if we multiply -5 times 251 over 495, I get negative 2.54. Okay, why is it? Well, you're losing, so it's negative. Now if I add these all up, I get negative $0.08, or negative 8 cents. Okay, so I'm gonna write the same sentence, pretty much. The expected value is negative I'm just going to write negative 8 cents, which means for every $5, you will be expected to lose 8 cents. Now, which one is better? Okay, so that's my interpretation. Which one is better for me? So I'm gonna say if you are playing for a long time, meaning you have like 8 hours to kill, which one would be better? Well, which one makes you lose less money would be craps. And so this one, the long time, is called the long run. You should play craps. Okay, in the short run, meaning you have one bet to make. You're like, okay, I only have $1. I have one time. I have 10 minutes. Which one should you play? You should play roulette. Why should you play roulette? Because you're expected to lose more money, but in the short run, it's a bigger gamble. Like, you win more money if you just bet once, versus over time you lose 26 cents every time you play. But if you've only played once, the gain is better. I know I'm teaching you guys gambling. Well, this is the end of the first set of notes. I'm going to continue the next set in a bit.